Hello. Today we're going to be talking about one of the sub-chapters in forces, mainly dealing with Hooke's law. Hooke's law is of course founded by the person Robert Hooke, which I have shown a picture here. And Hooke's law, okay, let me write it out here. Hooke's law basically says that in the case of a spring, let me draw the spring out. Of course, the normal encounter with a spring would look like that. You have many turns of a wire, and it has its own natural length, right? Let's say we start the initial position of the spring here, and this is the final position of the spring. And so this whole length here, it's your natural length. Okay, so let me put L naught. L naught, for the naught, you can assume that it's representing original, right? So original length. And if you extend the spring, for example, if you hang a mass, right? If you hang a mass and say you support it with your fingers first, right? You support it with your hand. If you release your hand, then of course the spring, logically speaking, will extend, right? This, I think, is intuitive to most people. Well, if I take again the initial position and the final position of the spring, right, the length now is a new length, right, an extended length. Of course, L prime minus L naught gives you the extension of the spring, right? Okay, so Robert Hooke did some experiments and he realized that the force that is used to pull the string down, let's subscript it as external. So external force used to pull the spring down, it's actually directly proportional to the extension. Right? It's directly proportional to the extension. Let me label it X here. Okay. So if I were to write in an equality, an equation, so this gives me the force that is used to pull the spring down. It's equal to constant of proportionality, let's label it at K, multiplied by X. Right, so K, we have defined it to be called the spring constant. Right. Well, if you're ever asked to define a spring constant, you can always rearrange your equation and you get spring constant is equals to force over extension. Right. So essentially spring constant is the amount of force required to cause unit length of extension. Unit, right? Let's deal with the units. The units of your spring constant, square brackets, it's usually can be used to represent the units of a physical quantity. In this case, the physical quantity, it's K, which is my spring constant. So the units of the spring constant is equal to, as seen from my expression here, Newton per meter. Right? Newton per meter. Okay. Okay, so if force, right, is directly proportional to my extension, then if I were to plot a graph, let me plot a graph of force and the extension. This is clearly a graph of y equals to kx expression. Well, I put the symbols here, y and x, meaning that y, it's the y-axis and x is the x-axis. In terms of Hooke's law, y-axis is represented by the force and the x-axis is representing the extension. Right? So y equals to kx graph will look like that. Right? Will look like that. Okay, so it's a straight line graph with a constant gradient and it's passing through the origin. Okay, so interpretation of the graph. I mean, if let's say, just as an example, if you want to extend your spring by say 10 cm, okay, so units is cm here, 10 cm, then this is Newton, right? So say this is 10 newtons to cause an extension of 10 10 cm. Then how many newtons will cause an extension of 20 cm? Well, you can predict it, right? Visually, it can be seen that it's 20 newtons, right? Okay, so 20 newtons will cause an extension of 20 cm. Okay. Now there is another characteristic that you can find by just looking at the graph. Okay, so this is again force and extension, right? It could be in meters, doesn't matter, right? Depending on the context of the question. So area under this graph, right? Area under this graph, you can see that it's your maximum force. Right, maximum force in a certain context, you reach a maximum value, and full extension, let's say, label it by x. The area under this graph, under the fx graph, let me label it here. Area under fx graph is equals to half f max multiplied by x, but f max has the expression of Hooke's law, which is half kx, right? Half kx, and this is x, so this gives me half kx squared. And what is a half kx squared representing in terms of a physical quantity? Let's give some brief derivation. Right, the area under this graph, it's force, right? It's force multiplied by the extension, and it's half, right? So you can see that this is actually the average force during the process of extension, during the entire process of the extension. Half F max gives you the average force. Average force multiplied by x is actually the work done, right? Work done on the spring. Right. There's some prerequisite knowledge required here, which is that work done is force multiplied by displacement in the direction of the force. Right. So this is the expression of half kx squared is actually the amount of work done on the spring. In terms of energy conversion, so the question is, after you have done this work on the spring, where is this work done on the spring stored? It is clearly stored in the spring, and the energy conversion is work done on the spring is used to increase or to store the elastic potential energy of the spring. Okay, so let me spell it out here. Elastic potential energy. Energy. Right? So my conclusion here is the elastic potential energy that's being stored in a spring is actually equals to half kx squared. Now these two formulas, one being the elastic potential energy stored in the spring, as well as your Hooke's law, which is here, and I've quoted this expression several times. It's the key formulas in Hooke's law subchapter. Okay, so all about springs. Just to leave you with some thoughts, extension to the concept is, if initially I have one spring, right, and now I have two springs, right, if I have two springs that are hanging like that, right, okay, and versus I have two strings that I hang in series, right, this is what we call series. How does this change the setup? What is the effective spring constant of the rightmost setup? And what is the effective spring constant of the center setup? Okay, I'll leave you with this question. Next video, I'll attend to these questions. Right? Okay, thank you.